that just means they don't share any common factors. And that's a lot of words, so here's an example. So this is a graph that has 3 vertices. We're going to label them 1, 3, and 4. So if you notice, like all of the labels that are connected by a line, those numbers don't share any common factors. So that's called a co-prime labeling. A prime labeling is essentially the same thing, except your labels can only be as large as the number of vertices that you have. And so what that means is, if we take that graph that had 3 vertices, we can only label those vertices with the numbers 1 through 3, but all of the adjacent vertices are still relatively prime to one another, and so we're going to call that a prime labeling. And that's enough background to get straight into the research question that we were tackling for this project. And that question is, how can we give prime labelings to grid graphs? So this is a grid graph. It's denoted p sub 5 cross p sub 3. That just means that it's a graph that has 5 columns of vertices and 3 rows of vertices. And there are some current findings on how to give prime labelings to grid graphs, or the kinds of grid graphs that you can give prime labelings to. So one result we have, we can give is for square grid graphs of size n plus 1. We know that we can give a prime labeling to a square grid graph of that form if it meets all of these conditions. So if n is equal to 5, or is equivalent to 3 or 9 mod 10, and additionally if n plus 1 squared plus 1 is prime. So that's a lot. But we also know that for grid graphs p sub n cross p sub n plus 2, we can give prime labelings to those when n is not equivalent to 2 mod 7, so a little less complicated than the last one. However, all the labeling processes for these grid graphs are just kind of complicated and weird, and I'll give you an example of one. Here's what one looks like right here. This is a square grid graph, 6 by 6. You'll see the numbers are just kind of all over the place. There's not a super pretty pattern to where they're being placed, but it is a prime labeling. And so what we wanted to do was find a way to give, again, like a prettier sort of prime labeling to grid graphs. And the way that we wanted to do that was by building off of prime labelings for a specific kind of grid graph called a ladder graph. This is what a ladder graph looks like. It's just a graph that looks like a ladder, so not super complicated. And we refer to that as p sub n cross p sub 2. And so I'll tell you all about how to give prime labelings to those kinds of graphs. But first I need to give you a quick informal sort of definition of a consecutive cyclic labeling. So a consecutive cyclic labeling of a graph, essentially you're going to pick a starting vertex. Our starting vertex in this case is in the upper left-hand corner. So you're going to label your starting vertex 1. And then you're going to label in an ascending order to the right until you hit the end of your graph, and then you go down, and you look back around to the 1. And that's a consecutive cyclic labeling. And so one of the findings that we were looking at with ladder graphs is that you can give a ladder graph a consecutive cyclic labeling that is also prime if and only if for the ladder graph p sub n plus 2, the number 2n plus 1 is prime. And that's a lot of words, so here is an example of what that looks like. So if we have the ladder graph p sub 3 cross p sub 2, what we do is we look at that 3, that's the part of the p sub 3, and we take 2 times 3 and we add 1. That gives us 7. 7 is a prime number, and that means that we can give this ladder graph a consecutive cyclic prime labeling that starts in the upper left-hand corner. This is what that looks like. It's the same as the graph that was on the previous slide. And then one of the other results that we looked at is if you can't necessarily start that consecutive cyclic prime labeling in the upper left-hand corner, can you still give that kind of labeling to the ladder graph? And you can, it's just a little more complicated. Before we were looking at 2n plus 1 for a ladder graph p sub n cross p sub 2. Now we're going to look at 2n plus p. P is a prime number that's less than 2n plus 1. And so your goal here is to find a prime number p such that 2n plus 1 is also prime. And if you can do that, then you can still give a consecutive cyclic prime labeling to a ladder graph. The starting vertex just won't be in the upper left-hand corner. An example of that would be p sub 7 cross p sub 2. So 2 times 7 is 14. You could add 3 to that and get 17, or you could add 5 and get 19. So there's different ways you can do that. Here's what that prime labeling looks like. This time our starting vertex is in the upper right-hand corner. And there are formulas that are dependent on that number p that help you figure out where your starting vertex should be. And so just as a quick aside, the proof that last theorem, just a consequence of that says that if every even integer 2n can be written as the difference of two primes, or the difference q minus p, where q is a prime and then p is either 1 or a prime less than 2n plus 1, then we can give a prime labeling to every ladder graph. And then that will bring us to the results that we got into with this project. So to start with, we're going to talk about the results we have of that difference of two primes problems, but then we're going to transition and look at different ways we can give prime labelings to grid graphs. We're going to further separate that into something we call a vertical path consecutive labeling and something that we're going to call a horizontal path consecutive labeling. But first, the difference of two primes. So what we did to investigate that problem was create a program in Python that would check for pairings of prime numbers. And so what it does is it will generate a list of prime numbers, and then it will calculate p equals q minus 2n, and it will check to see if that's either equal to 1 or a prime that is less than 2n plus 1. And so using that program, we were able to find pairings of prime numbers up to 2n equals 2 million. That did take us 3 days to run that program though, so we did a bit of a snag there. But what that does tell us is that for every n that's less than or equal to 1 million, we can give a consecutive cyclic prime labeling to the ladder graph p sub n cross p sub 2. And so moving on from that, we wanted to look at giving labelings to grid graphs. We only looked at grid graphs with 3 rows. One of the first things that we noticed is you can't really give it a consecutive cyclic labeling like you can with the ladder graph. So we had to come up with new patterns to label these graphs with. The first thing that we looked into was a vertical path consecutive labeling. And so here's an example of what that looks like. We're always going to restrict our starting vertex to be in the upper left-hand corner. So you're going to label that with the number 1. Then you're going to label in an ascending order down your graph. So 1, 2, 3. Then you move over to the right, up till you hit the top, over to the right, down to the bottom, over to the right. And it'll just keep continuing that pattern over and over again. And so the cool thing about that kind of labeling is if we're following that vertical path consecutive labeling for a grid graph p sub n cross p sub 3, every vertex that's in the middle row of that graph is going to be relatively prime to all of its neighbors. So it won't share any common factors with any of the vertices that it's connected to. And so we were continuing on with that kind of labeling, and it was prime up until the grid graph p sub 5 cross p sub 3. Here's what that graph looks like. So we have a problem here. 10 and 15 are next to one another. So 10 and 15 are both divisible by 5. So that means that they aren't relatively prime, and this isn't a prime labeling. However, hopefully you'll see we also have labels A and B here. So if we actually swap the labels on those vertices labeled A and B, then we'll wind up with a graph that has a prime labeling. So here's what that looks like. It essentially follows that vertical path consecutive labeling, except we're just switching out the problematic vertices. So we have sort of a system that'll give us close to a prime labeling, and then we're just switching out the problem spots. And so in general, we found when following this kind of labeling, every label that's a multiple of 15 will be adjacent to a label divisible by 5, and so that kind of wrecks our prime labeling. But for some smaller grid graphs, we were able to just swap out those problematic vertices, like in that example. And we were able to do that for ladder graphs, or grid graphs up to p sub 40 cross p sub 3. And so moving on from that, we wanted to try a different kind of labeling. Before we were looking at a vertical path consecutive labeling. This time we're going to look at a horizontal path consecutive labeling. And so that's very similar. Our starting vertex is in the upper left-hand corner again. But this time we're going to move all the way to the right until we hit the end of our graph. Then we're going to go down, move all the way to the left, down all the way to the right until we get to the end of our graph. And the nifty thing about this sort of labeling is that it's actually just a hidden ladder graph that we're adding an extra row to. So it's easy to just build off those previous results that I talked about earlier. And so what we found with that is for a grid graph p sub n cross p sub 3, it's going to have a horizontal path consecutive prime labeling if and only if the numbers 2n plus 1 and 4n plus 1 are prime. Again, a lot of words, so here's an example. This is the grid graph p sub 3 cross p sub 3. So 2 times 3 plus 1 is 7, that's prime, that's wonderful. 4 times 3 plus 1 in this case is 13, which is also prime, and so this gives us a prime label. Now I want to get into like why this is true, but I'm going to give y'all a quick break from the math for a little historical aside here. So I want to talk about the Sophie-Germain prime numbers. So Sophie-Germain prime numbers are the set of prime numbers n such that 2n plus 1 is also prime. An example would be the number 3. That's a prime number, but 2n plus 1 is 7, which is also a prime number. And so we're looking at 2n plus 1 and 4n plus 1. So the set of prime numbers n such that 2n plus 1 and 4n plus 1 are also prime is going to be a subset of those Sophie-Germain prime numbers. And so you may be wondering, who is Sophie-Germain? Well, here's Sophie-Germain right here. She was an 18th century French mathematician and physicist. As I'm sure you can imagine, it was not ideal to be a woman mathematician in the 18th century. And so she often hid her name and her gender using pseudonyms so that any of the work that she did would be taken more seriously by the mathematicians of her time. She was mentored by Gauss. If you know anything about Gauss, he laid the foundation for so many of the rules that we use in algebra. And she did coordinate with him and would correspond with him, writing letters back and forth, usually having to do with number theory, which she did most of her work in number theory. Number theory has modern applications in things such as cryptosystems. If you're familiar with RSA, that's a very common cryptosystem that's in use today, and its encryption process relies on prime numbers, so that's also related to what the prime numbers that she was looking at. And so that is the end of our historical aside. We're back to the mathematics now. So here's the theorem that we were talking about before. We want to show that this is true. We want to show that this has a horizontal half-consecutive prime labeling if and only if 2n plus 1 and 4n plus 1 are prime. And so if you don't know exactly how the math proof is structured, this is called an if and only if statement. So you have to prove it both ways. You have to prove that if the first part is true, then the second part is true, and if the second part is true, then the first part is true. And so proving the first part is true is called the forward direction. So for the forward direction of the proof, what we do is we assume that 2n plus 1 or 4n plus 1 is not prime, and that's proving by a contradiction. And so here's how that proof works. We've got this graph. This is our general gray graph of size p sub n cross p sub 3. You go 1 to n for your vertices, go down, and then over until you get to the number 2n, down and over to 3. And that's one way to think about how to give a general labeling to these kind of graphs. But another way to think about it is to just isolate a single column on that graph. And if you do that, you can think of the top label as just some number a, and then the middle is just some number b, and then finally your last label will be given by 4n plus 1 minus b. And that 4n plus 1 minus b is sort of the focal point of this proof. So at the beginning of the proof, we assume that 4n plus 1 wasn't prime. So if that would mean that there has to be a prime p that divides 4n plus 1. So if that prime p is on the middle row of this graph, then our labeling isn't going to be prime, because 4n plus 1 minus p will be next to p, and the greatest common divisor of those two things will be p. And that's also a lot of words, but the main takeaway here is that you cannot have a prime labeling if that is the case. And so we were able to show that for p being on the middle row. We were also able to show that if that divisor p is on the top row, a multiple will also exist on the middle row, and so this case will also hold here. The second part of the proof is called the backwards implication. And this one's a lot easier. We're just going to assume that 2n plus 1 and 4n plus 1 are prime. We're following our same procedure that we were looking at before. So 4n plus 1 minus b will be next to b in this case, but their greatest common divisor is going to be 1 for all labels b, because 4n plus 1 is prime. And so that's all we have to do there. And just as a note, you'll probably notice that we weren't working with that 2n plus 1, and that's because the graphs that we're looking at are just an extended version of our ladder graph, and so that 2n plus 1, every case dealing with that, is already covered in the theorems that are talking about the ladder graphs. But that brings us to the future work we want to do on this project. So as far as the difference of two primes problem, we want to run that for larger values of 2n. It did take us 3 days, like I said before, so we'd have to find a way to sort of streamline that process, so it's a bit easier. We also wanted to see if there was a pattern that worked for p set equal to 1 to see if we can build any of labeling. For the vertical labeling, if you'll remember, we're just swapping out the problematic vertices, but we didn't have a rigorous process for that. So if we could find that, that would be amazingly helpful. And for the horizontal, we would like to extend that to more general grid graphs of size p sub n cross p sub m instead of just p sub n cross p sub 3. Here are my references for this project. I want to say thank you to Dr. Caitlin Phillipson for being my advisor and to the St. Edward's Math Department, and thank you all for listening to me. Encryption and modern crypto systems, so there's no application now, but there might be at some point in the future. It happens a lot in math where you just kind of do something and then later you figure out what it's good for.
Have you ever considered like bounding the number of problematic vertices? Like, is there a maximum number of problematic vertices that could appear in a graph?
Well, every label that's a multiple of 15 is going to be a problem. So just kind of be a problem forever.
That's the only class of problematic vertices?
Yeah, those are the only ones.
You didn't say mine. Well, so as you know, one of the most basic questions coming out of number theory from a long time ago is prime factorization. And I don't want to necessarily want to add to your future work, but has it ever sort of occurred to you maybe to look at whenever you have a particular grid graph with a particular kind of labeling, maybe focus on some larger label and say, hey, what's the prime factorization of this, and look at where those primes may be located within your particular grid graph in terms of patterns. Of course, it depends on what kind of grid graph you have, obviously.
Yeah, I'm not totally sure that we did anything like that, but that would be a good avenue to explore and keep looking at our problem.
Yes, this might be a silly question. Math person, but is there typically like multiple ways to do prime labeling, or is there only one way?
No, there could be multiple ways to do prime labeling, so let me give you an example real quick. Sorry, it's kind of far back. Okay, so like this graph here. What this theorem is telling us that I talked about earlier is that if that number 2n plus p is prime, then you can give a prime labeling to this. There are different values you can use for p though, and there are, depending on that value p, there are different locations you can place your starting vertex. So just off the top of my head, there's two different values for p that you can use. So that would give you two different starting vertices, which would give you two different prime labelings for that graph. So there can be multiple ways to give a prime labeling.
Any other questions?
It's just a little math note. It's not the Goldbach conjecture. If you don't know what the Goldbach conjecture is, it's a conjecture that says that every even integer can be written as the sum of two primes. Mine is looking at the difference of two primes, and there's bounds on one of the numbers. So it is not the same as the Goldbach conjecture.
Silver ball.
We met in fall 2019. Marci sophomore year, which meant I was also correct. Like, I just made a bit of math major into 3 years instead of usual 4. So Marci had to take math classes together that we would never wish that was going to be. Like, she had that, like, just the most intense math person that I've seen here so far. And in the middle of that, like, we're at the beginning of that, COVID happened, is Marci had to take pretty much whole math major online until this year. And man, she handled it, you know. And I'm so impressed with her coursework and how she's handled that and just clawing her way through that process. And as far as being her research advisor, it's just been such a delight to see Marci go from, you know, a math student to a math major to a math physician. And the way she can just walk us through research and pull the research